more formally is because we're only looking at single value domains, where you're only interested in your interesting set, means that if you have a better type, or if you have a certain type where the allocation, so if you have, so if theta I is allocated, right, is interesting set, then if the same agent would report a higher type, theta prime I, he should also be allocated, where there's this ordering given here, which means that, well, it's unfortunately easier to have this as smaller than presentation, but it's what I said before. So you have better type if you have early arrival, later departure, or high value. Okay. So this is an example. Okay. So suppose theta I is like this. So you arrive at time slot 1, you depart at time slot 2, your value is 1. Right? So this agent is not allocated as interesting set. Suppose an agent would say this report and report an earlier departure time. If he is then allocated, that violates monotonicity. Or any of these other two. If he would say report a later arrival, or he would report a low value, all of these examples would violate monotonicity. Okay. So now let's look at a simple example, and then I'll let you do some work on this, because this is quite interesting to get the intuition. Okay. So we look at this setting here, where we have two time slots, same setting I had before. At every time slot, there's one resource available. We have to auction off this one resource. So there's one resource available at time step 1, and one resource at time step 2, and let's assume perishable. So this resource disappears if we don't allocate it immediately, right? For the kind of the electricity setting. Now there's these three agents in the market. This agent here only arrives later with value 0.9. This agent arrives immediately and stays for 2 time slots with value 0.7. And this agent stays for 1 time slot, the first one, and has value 0.5. Now these kind of allocation problems, so resources come available all the time, like the computational resource, electricity. Agents arrive over time. I don't know if you've noticed, but it's a scheduling problem. Right? So it's online scheduling. So this is called online scheduling problem. And a famous heuristic in online scheduling problem is allocate the resource with the person with the earliest deadline first. Okay? So with online scheduling, it's the same problem. You have to make decisions right now without knowing for sure the future. And so therefore, what a heuristic is used in that is called earliest deadline first, which means that allocate the resource of your earliest deadline, because if an agent is more flexible, we can see what happens in the future, and then we can decide whether we allocate something to this agent in the future or not. Okay. Does everyone understand the earliest deadline first? Okay. So just we can do this part together. Okay. If we apply this earliest deadline first schedule, who would get which unit? Yeah.
So yes. So at time step 1, we don't know that the third player is going to come at some point later on. So we will allocate the first time slot to the player with the smallest flexibility, which is the bottom player. We raise 0.5.
Agent 3. Yeah.
So we will wait for the future to see what happens with player 2.
Yeah.
The second time slot, player 3 arrives, who pays more. So we will allocate player 1 actually. Yeah. So we will allocate the slot to him, and player 2 will get nothing.
Okay. Any comments about this protocol? Is that earliest deadline first? Yeah.
It is, but we break the ties according to the
Yes.
values.
Okay, so earliest deadline first does not look at values at all, right? It only looks at the departure. So in scheduling, you don't consider values. So at this point, these depart at the same time. So you have to have some sort of tie-breaking rule. Okay. And we're not allowed to use values in the earliest deadline first heuristic. So what we could either can have a random tie-breaking rule, or we can have a predefined order of agents, say 1, 2, 3, right? And if there's a tie-break, then I give agent 1, say, priority. Okay. So just to make it simple, we'll not look at random tie-breaking rule because then we have randomized mechanism, which is a little bit more complex. So that's true that this agent does get the tie-break. Okay. So this kind of tie-break where the person with the highest index gets the outcome. Okay. These two questions we have to now, you guys now have to answer. Okay. Right, which is could be tricky, but you can ask me any questions you want. So, does this social choice function satisfy monotonicity? Yes or no? And the second prize is, can we design payments to incentivize truthful reporting? Yes or no? Can we find any sort of payment that the agent will be incentivized to truthfully report? Okay? So you just need to fiddle around. So to answer this first part is we have to find a type, say one of these agents, okay, should be able to report a worse type, a lower type, and get better treatment. Okay? So I guess we could do that together. Yeah.
Well, agent 2 could easily just say that he only has time period 1, getting good chances as agent 3 too. Because as it is, he has no chance of actually being a sent.
Okay. Yeah. So that's right. Does everyone see that? Okay, so if this agent misreports and says, okay, I want to, I'm only available at time step 1, this agent gets assigned. Why does that break monotonicity?
As he is given a great evaluation, and even though someone else was given a low evaluation, it's the same start time, gets it indefinite.
Yeah, you could see that like that. Yeah. But it even breaks, so even if you didn't have this agent, well, because, so you could even have it say, okay, what if this agent would be different, replaced by different agent, which is actually has less flexibility, it would get allocated. Whereas an agent which has more flexibility, in this, the real agents that's here, is not going to be allocated. Okay. So that's kind of the key here. So is that's kind of, see, so this is how you break monotonicity. So what kind of payments, so we can say, okay, it doesn't matter, we don't care about monotonicity. Could we find a payment that incentivizes truth telling for this strategy anyway? Right? So the current social choice function is that this agent gets a slot. So V3 gets a slot, and V1 gets a slot. Okay? So that's the, if we have a social choice function, which is called earliest deadline first, we get an allocation where agent 3 gets a slot 1 to be precise, and agent 1 gets slot 2. Okay. Can we define payments that satisfy incentive compatibility and individual rationality as well? So what could we do, right? So this guy, what could this guy pay, right? So this, whatever payments we design, if we want to maintain individual rationality, we cannot charge this guy more than 0.5. Right? Whatever payments we design, let's look at all possible payments. Forget about DCG over there. Okay? So if we could design any payments we want, we could never charge this guy more than 0.5. Okay? So it can be at most 0.5. So, however, for 0.5, this guy wants that slot. Right? If the slot is going to be 0.5, then this guy is going to be wants that slot essentially. So we already said that this guy can easily manipulate in order to get this item. But if this guy, if the payment is too much so that he doesn't want the item, no, he wouldn't want to manipulate. So the question is here, can we still find payments where this whole thing is truthful? And the answer is obviously no. Okay. So, but let's. So what we see here, there's earliest deadline first. We've looked at the social charge function, earliest deadline first, and it breaks monotonicity. And because of that, there's no possible payments that we can design for the agents to be truthful because of the monotonicity break. So this brings us to a theorem that I won't go into the proof, but it's not actually that difficult, which says monotonicity is a necessary condition for any social choice function to be truthfully implemented. So necessary means that we need this condition, and we may need additional conditions as well. But if this condition is violated, we cannot get truthfulness for sure, at least in the general cases. Okay. It turns out that in certain times, it's actually the only condition that's needed. If we satisfy monotonicity, we can get truthfulness. And when is this? When is it possible? When we have a known interesting set. So if we know, say, what the agent wants, it's just we don't know their value, we don't know their arrival and departure. In that case, we can always truthfully implement. So that means dominant strategy is compatible. So we can design corresponding payments to the social choice function f, as long as we know the interesting set. So that means that as long as the allocation policy is monotonic, so it does not violate monotonicity, we can always find the corresponding transfers which ensures that the mechanism is dominant strategy set compatible. So essentially we don't have to care about the payments too much, but we'll look at what these payments are in a bit. But the problem is not the payments, it's actually finding the allocation policy. And then there's a very easy way to find the corresponding payments. So we've reduced the problem quite considerably. We just have to look at, let's look at an allocation policy, but we have to look at this monotonicity. Okay. And then I'll give you two examples which satisfy monotonicity. Okay. And we'll look at those in more detail. So these are first come, first served. So what does that mean? So allocate the resources to the unallocated agent who arrived first. And for example, we have again time rating rule. Greedy. So greedy, allocate the resources to the unallocated agent with the highest value currently in the system. So the first come, first served is a bit like the earliest deadline first, in that it does not look at the value of the agent at all. It completely ignores the agent's value. It just looks at when the agents arrive in the market. Greedy, on the other hand, does look at the value of the agents and doesn't look at when the agents arrive, and also doesn't look at the departure of the agents. Okay, so it just looks at the value. Okay. So let's do this example here. So the allocation, so first come, first served, who gets the allocation? Who gets one item? So agent 2 gets an item, and anyone else? Yeah.
And agent 3.
And agent 3. Really?
First.
Yeah. And agent, actually that's true, yeah. Agent 2 gets an item. No, actually.
I mean, it's
no. Agent 1.
Do not say first come, first served.
Yes, first come, first served.
yeah, but the time that you allocate the highest the agent 2, then the other one gets like start, it's also to do. I mean, it meets the deadline without being allocated, and then the other one
Yes.
comes with a higher value.
But the value we don't care about. Right? So first come, first served, right? What happens? So these ones, so we said we would break ties according to the index. Okay. So in this case, so these arrive at the same time. So at this point, agent 2 gets allocated at this point. Okay. Here we have another item, but now this guy is no longer in the market. Okay. So so then this guy's only one in the market, so we allocate the item to this agent 1. Okay. So does this break monetaricity? Well, what? So obviously it doesn't look at the value, so we can change the values what they are. They won't have effect on the strategy. So it's monotonic in the value. Could any agent benefit by reducing its arrival and departure? Could they?
Even reducing or extending?
Ah, okay. So if we extend it,
For example, if the agent 3 extends his departure,
yeah,
then it would be selected.
yeah, you would be selected, yeah.
But you can't extend your departure.
You can't, well, suppose you could, right? You could, in some cases you can, but yeah, we assume that normally you can't. But suppose what would happen if he could? He would be allocated at this point. He's not really in the market, so he's not able to receive goods, right? So his true departure is here. So he's going to get goods. So he gets allocated the energy, for example, but he's not, his battery is not there. So he's not going to get it, right? So if he could extend his deadline and then get allocated here, because he extended, if you manipulate it in a way that he could get allocated here, then okay, then it would be beneficial to him. But he can't, right? The only thing he can do is extend the deadline, but then he gets allocated here, which means that
Yeah, or even the other could win because it has a higher value.
yeah,
Well, you could have secondary market issues, though, depending on the application.
yes, it depends on the other application. Yeah, but we've assumed at the beginning, I guess, yeah, that can't be done. But yeah, you're right. In certain cases, you could have you can manipulate by extending your deadline, if that's possible somehow. Okay, so that's the first come, first served. So we can see that that's already an allocation we cannot manipulate. Right? So we can't change and be better off. Okay? Even if the fact that we don't have transfers here, we don't have any payments. And already we can see we cannot manipulate. So with greedy, that's a different story, in the sense that we are looking at the values. Okay, so who would get what when we do greedy allocation? Agent 2 and agent 1. Yeah. Okay. So greedy, what it does is as follows. It looks at every time step individually, looks at, okay, who needs an item in this point in time, choose one. And this time, agent 2 has the highest value. So let's allocate agent 2. Then it moves on to the, so it's very myopic in a sense, right? It doesn't really look at the future at all. At time step 2, it looks again. Here, this agent already has a value, so its value for getting another item is 0. The value of this agent, it hasn't got any value yet, it's 0.9, so greedy then allocates to this agent times step 2. Okay. So this, in a sense, because it doesn't take into account arrival or departure, it just looks at who's in the market at this point in time, and let's allocate it. So it doesn't, in a way, it does take into account arrival departure, because it doesn't allocate to anyone who's not in the market. So that means that if you're in the market for longer, you're going to be more likely to be allocated, right? Because the greedy mechanism. If you have a higher value, you're also more likely to be allocated. So it satisfies monotonicity. Because if you have more flexibility, you're more likely to be allocated. And if you have a high value, you're also more likely to be allocated. So this really also satisfies this monotonicity. So what's missing here to get greedy incentive compatible is transfers, so payments, right? If there's no payments, obviously B3 will misreport and say I've got a value of 10, right? That's obviously the case. So for greedy, we do need some sort of payments. So what payments could we get here, which would make them incentive compatible? So that's an exercise. Okay. So what could we charge V2 and V1 so that there might be incentive compatible? What's your intuition there? So that there is incentive compatible. Let's discuss. So maybe let me give you 2 minutes to discuss it amongst yourselves. Okay. So discuss. So what payments could you have here so that the agents are truthful, and we'll all look at the greedy mechanism. Okay. So let's just discuss amongst yourselves. Puzzle. So the intuition is here similar to what we see with the BCG option, a little, not quite the same.
As long as you pay what you declare, should happen.
Really? Okay, so so B2 then pays 0.7 because it declares 0.7, right? So why wouldn't it declare 0.6? It would be better off.
Because he doesn't know what other agents are there.
Yeah, suppose he knows everything. So we're looking at dominant strategy instead of compatibility, which is nice because we can assume we know everything about the other agents. Even if we know everything about the agents, it should still be incentive compatible. So we have perfect information. As an agent, right? The market doesn't know anything, but the agents do know everything. Let's assume.
Yeah, but in that case, if it's better for the agent to say 0.6, then for the 3, would be better to say 0.7.
Yeah. No, but it's not incentive compatible. So the payments where you report, but you have to pay what you reported. It's not a good mechanism because it's, as we say, it's not the truth. So what could be truth?
Second, you pay second highest bid.
Yeah, kind of, okay. So what would that be here for the agents? I mean, for both agents, okay? For agent 2, that will be 0.5. So what would be agent 1 paying? 0. Okay? And can they manipulate?